Hi, welcome back to Fat Mama Physics. In these videos, we are going to talk about potential energy, gravitational and elastic, which warrants for two videos. This one will be on gravitational. The second one, we will talk about elastic potential energy. So just in brief, what is potential energy? Oftentimes you would hear the word when someone would tell you, oh, you have lots of potential to become blah, 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 blah. But then we can't see that right now. It's not something that it's manifesting itself. So then what does that mean in terms of physics? Potential energy has the ability to do work, has the ability to be converted to other forms of energy. We call that stored energy. More specifically, gravitational potential energy is an object's stored energy due to its position in a gravitational field. We know Earth has its own gravitational field, the Sun has its gravitational field, dark holes has its gravitational field. With gravitational potential energy in this unit, we'll be dealing mostly with cases on Earth. So what is the equation for that? Gravitational potential energy, EP, equals to mgh, which m is the mass in kilograms, g is the Earth's gravity, or acceleration due to gravity, which is just 9.81 meters per second squared. It's unlikely to be dealing with other cases and on other planets. And last but not least, h is the height that the object is above an arbitrary reference point. Most of the time we'll be dealing with a flat ground, and an object is some height above the ground. Usually that's where we choose our reference point to be. This equation mostly works for heights that are near the Earth's surface, which the gravity is roughly 9.81 meters per second squared. Anything higher than that, then the Earth's acceleration due to gravity will decrease, which that's a different case and warrants a different equation. So we'll be mostly dealing with these ones, near the Earth's surface. Also, notice that we've seen this in a previous example in this unit, where the work done on an object to lift it up was the force due to gravity times the displacement in the upwards direction, or mgs. And then in this case, s was the displacement, but then it's kind of the same thing as height. It shares the same dimensions. So if I do work on an object, I can increase the object's potential energy. Something to think about. And since this is a potential energy, is a form of energy, energy is measured in units of joules. So let's get on to some examples. Okay, we have Jimmy is sitting on a roller coaster that lifted him from the ground up to point A. And it did so at constant velocity in the diagram on the right. So imagine Jimmy was here and the roller coaster pushed him, the ride got him all the way to the top at point A. Question A, how much potential energy does Jimmy have at point A? So we do have Jimmy's mass. We have the acceleration due to gravity, which is 9.81. And we have the height here, which at point A is 200 meters. So if we're just looking for potential energy, that's EP equals mgh. We have all our values, and we can just substitute everything in. Multiplying everything out, we get 174618, which rounds to 2 sig figs, 170,000 joules. Lots of joules, but won't make Jimmy rich. All right, so B, and that's pretty straightforward. But let's take a look at B. How much work was done on Jimmy in lifting him up? And I'm assuming that's to point A. We know that the work done on an object is equal to that object's change in energy. Well then, let's take a look at what kind of energy Jimmy is gaining. Jimmy is gaining potential energy for sure. What other forms of energy is Jimmy gaining? Well, the roller coaster might be accelerating him, so he could be gaining kinetic energy. But here in the question it says he is going from point A to B to ground up to point A at constant velocity. If he is not gaining speed, he is not gaining kinetic energy. So there is no kinetic energy gain here. So since Jimmy's only gaining whatever potential energy he would have at A, then the work done on Jimmy would be just his potential energy that he gained in question A. Wow, you didn't have to calculate anything. And that is the essence of a lot of questions in this unit, because a lot of them are more conceptual. You might be wondering, oh, can I just write 170,000 joules instead, and that I just be done with it? You do need to show some work and some understanding that the fact that the amount of work done on Jimmy is equivalent to whatever energy change Jimmy is experiencing. And since it's just this change in potential energy, writing what we have here is enough. Okay, so that is a B. Well, let's move on. Oh, the question continues. We have a diagram here, and I'm just going to write Jimmy's mass. And hey, this is a question you can probably do. Question C, how much potential energy does he have at point C? So this is a good time to pause the video and try it out. And now I'm going to quickly go over it. So we know at point C, the height Jimmy is at 160 meters. So if we use EP equals mgh, we have his mass, we have gravity, his height is 160 meters. Putting this all in our calculator, we get 139,694.1. Rounding to two significant figures, we get 140,000 joules. Okay, not bad, eh? Now for D. Oopsie, that should say E here. How much potential energy does Jimmy lose going from point A to point C? Well, we know that at point A, Jimmy has 174,000-ish joules, 100,000 joules, and then at point C, we just calculated that here. What we want to find here is how much does Jimmy's potential energy change going from A to C? Notice he has less than C since the height is smaller. So how much potential energy that he loses is the difference between his potential energy at A and his potential energy at C. So that is 174618 minus 139,694.4 joules. Making sure we don't lose any significant digits. And we get 34923. And that rounds up to 35,000 joules. We don't need to write a negative sign because the question already says it's assumes it's lost energy. Well, lost potential energy, not lost energy. You might be wondering, oh, if Jimmy loses that potential energy, where does that energy go? Aha, we're going to talk about that in the next question. Question E. Oh, and this is F here. How much kinetic energy would Jimmy have going through point B after starting off at rest at point A? Assume the roller coaster does not lose any energy going from point A to point B. And what I mean by losing any energy, due to friction, thermal energy, heating up the tracks, those kind of things. So what is going on when Jimmy goes from point A to point B? Well, I'm pretty sure you've been on some sort of roller coaster ride in your life, hopefully. So then what would happen is at A, he has a lot of potential energy, and as he makes his way down to B, he will start losing that potential energy, but then that potential energy is going into kinetic energy, allowing Jimmy to go faster and faster and faster into going down to B. So then we have a lot of potential energies to start with, and slowly that's being converted into kinetic energy, which at B, since it's at a height of 0 on the ground, Jimmy's going to have 0 potential energy at B, but then he's going really fast, meaning he has a lot of kinetic energy at that point. So in this process, we have a conversion of potential energy into kinetic energy. So whatever potential energy Jimmy had at A is going to be all of the kinetic energy he's going to gain at point B. What this is Jimmy's potential energy at A is going to be converted, all of it converted to kinetic energy of Jimmy at point B. And since there is no loss of energy due to friction forces and air resistance, then we have a complete energy transformation here. So since the roller coaster will not lose any energy due to friction or air resistance, all of Jimmy's potential energy at A will be converted to kinetic energy at B, where the height is 0, and so the potential energy is 0 at that point. So we get a complete conversion, in which the kinetic energy at B will be 170,000 joules, the same answer you found in A. So in this question, please don't just write the answer. Have a little bit of an explanation here on why it is the same answer as A, if you were to do this question on a quiz or test. Okay, so F, last question, I think. What would Jimmy's speed be in question D? Okay, so at point B, we want to find Jimmy's speed. Well, we do. Now it's probably a good time for you to think about what to do, and you've learned everything that you need to learn up to now to know how to find Jimmy's speed. Good time to pause the video to try it out. Aha, okay, so it is my turn to show you. First of all, we know Jimmy's mass. We also know his kinetic energy. His kinetic energy at B without rounding is 174618 joules, just like his potential energy at A. And we want to find his speed. We do know that kinetic energy is, the equation for that is 1/2 mv squared. We have the kinetic energy, we have the mass, we just need to solve for the speed. So let's do that. First multiplying everything by 2, then dividing both sides by mass, then taking the square root. We get the speed is a square root of 2 times the kinetic energy all over mass, so putting all that in, and into the calculator, we get 62, or that's 60, rounding up to 2 significant figures, 63 meters per second. Okay, so that's question F. And that's the end of the examples. And this video, which we doing a quick recap, all we did was introduce gravitational potential energy, seeing how to calculate it, how that you can increase gravitational potential energy by doing work on your system, how gravitational potential energy can increase and decrease, and when it does, that energy goes into somewhere, gets converted into sometimes kinetic energy we can then calculate. We are going to talk more about conservation of energy, not in this lesson, but in a later lesson, which we will talk about multiple forms of energy that might be involved in the system. But for today, this is all we have and all you need to know. I will see you in the next video, which we will talk about elastic potential energy. Thank you for watching. Fat Mama Physics signing out.